All right, let's go ahead and start. Okay, I want to finish up the amino acids today because there's only 3 of them. So that'll be nice. So after today, no more amino acids, except that they'll be on the exam, but no more new ones. This first one here is histidine. This one is one of your basic amino acids because it has these basic nitrogens in there. It has hydrogen bonding because of the NH. And in the body, you tend to have a positive charge, which is right, usually like on that nitrogen right there. This is an essential amino acid. This helps with zinc excretion. It also, histidine, what does that kind of sound like? Histamine. And it's a precursor of histamine. So that's why it probably sounds familiar. And when histamine, what do you think of? Yeah, and allergies and yeah. Histidine has also been shown to help with sexual enjoyment for those of you who care. So I always joke, yeah, now all of a sudden everybody, they're going to sell out of histidine in the bookstore now. But anyway, they've done a few studies and they found that it has enhanced sexual enjoyment. The last 2 are the negatively charged R groups. These are very, very similar. Aspartate and glutamate. Sometimes you hear it called aspartic acid or glutamic acid. So do you see right here this COO minus? Whenever that has an H there, that means it's a carboxylic acid. And that's when it's like aspartic acid, glutamic acid. So before it reacts, it's the acid. And so when you hear it called aspartate or glutamate, that means it's reacted. It's already lost its hydrogen. So those are it's the same thing. It's just you're specifying that it lost the hydrogen already when you end it in 8. So these are negatively charged. They're acidic, but again, as it's showing after it reacts as an acid. But these are acidic with carboxylic acids. These in names are similar. Do you see this is a CH2 carboxylic acid, and glutamate is CH2CH2 carboxylic acid, which is very similar. Let me go back. Yeah, glutamine and asparagine. Good. So here's glutamine. Oh, sorry, this one's, I went on asparagine. So this one's asparagine, which is just like aspartate. Okay, so this one's CH2 amide, but the other one, aspartate, is CH2 carboxylic acid. And then over here, glutamine, CH2CH2 amide, and glutamate is CH2CH2 carboxylic acid. So the names are similar because the structures are similar. It just does it end in a amide or a carboxylic acid. But the beginning of the name is the same. So these are acidic, negative charge in the body after it reacts. This carboxylic acid can further react and form those peptide bonds. So anytime you have the amide or a carboxylic acid, you can further the peptide bond. So those are another reason why aspartate and asparagine and glutamate and glutamine have a similar name, because all 4 of those, you can prolong the peptide bond through the R group. And those are the only 4 that can do that. This is used in the urea cycle. It's also been shown to help with stamina and brain activity. This one's also good for like toxin removal, especially like ammonia from the liver. And if we look at glutamate, this one's very similar. You just add the extra CH2 group. And this one's a neurotransmitter. And it's also been used in learning and like memory. It's also a food additive. Those are all of the amino acids. So again, be able to draw them. So the top of it, every amino acid is the same. It's the R group that's different. And be able to recognize the functional groups, their intermolecular forces, and you can tell by just looking at those. And when I say functional groups and intermolecular forces, I'm talking about in the R group. Okay. And also their grouping. Are they considered in the nonpolar group? Are they in the aromatic group? And so if I show you, the slides that look like this tell you the groups. This is the negatively charged acidic group. And then if we go back, it's the slide that has the summary of all of them. Here's our positively charged basic group. And then polar uncharged group. Anyway, so you can go and look at all those. So it tells you the grouping. So know the classification of each amino acid. And if you can get this down really well, not only will it help you with the exam, but in biochemistry, he pretty much expects you to already have these memorized and know, like, you have this down. He doesn't spend a lot of time on these. He assumes you know them. So it's better to get it now than playing catch up in biochemistry whenever biochemistry is hard enough. You don't want to have to play catch up. So. Yes. Yeah. Well, actually, it's under week 1, I think. Oh. But I'll look and make sure. But I thought I saw it the other day there.
Oh, okay. I didn't go to week 1.
Yeah. It was a long time ago. If you don't see it, let me know, and I'll post it on week 6 that we're on. Yeah. Week 3? I know, like I saw like on one of the earlier weeks.
I just started from when we started, and I didn't go back to the first. Oh. Oh, thank
you. Okay, so we're going to learn a little bit about carboxylic acids this first half of the lecture, and then the second half we'll start reviewing. I did post a sort of review on sampling if you want to try that. I don't know, it has like 15 problems or something. Remember to also study like the homework problems, the other homework problems I have on there, and any problems we work out in class, stuff like that. Yeah, so that should help. So that's already posted for you to look at. Okay, so carboxylic acids, what does that look like? Yeah, a carbonyl with an alcohol. So you see here C double bond O with OH. Sometimes you'll see it written, you've probably seen this a lot, it's written as COOH. If you see COOH, that they're just kind of being lazy, whatever, they're not showing all the bonds, but that means carboxylic acid. Aliphatic, this just means it has a long carbon chain on it, okay? So you would have like 5 carbons, and then at the end, your carboxylic acid. And And the aromatic, obviously they're going to have a benzene on there. Okay. Naming. These, you're going to have your base name, like ethane, propane. You're going to drop the E, like we've been doing, and it's going to end in oic acid. So if we look at, let's look at one of the simple ones, like right here. What is the longest continuous chain? 2, right? How do you say 2? Ethane, so that's ethanoic acid. Carboxylic acids are always at the end, kind of like aldehydes are always at the end because it has to have the hydrogen there. Carboxylic acids are always at the end because they have the OH. So you never have to put what number because they're always number 1. You can see if you look at all of these, has the carboxylic acid portion in green. Notice it's always at the end, always carbon number 1. So let's look at this one here. What's the longest continuous chain? And you can't, like a cyclic is something completely different. Like this is, like you can't go 1, 2, 3, 4, 5, 6, 7, 8. Okay. So the longest chain here that includes the carboxylic acid would be 3, right? So how do we say 3? Propane. So with the carboxylic acid, it's propanoic acid. And then what's this group right here called? Not benzene. Cyclohexane. So this one, remember whenever it's a branch, it ends in ol, YL, kind of like methyl instead of methane, or ethyl, or propyl. So this is cyclohexyl instead of hexane. And that's carbon off carbon 2. For this next one, the longest chain is determined by which chain will include the most functional groups. Okay? So you say, I could go 1, 2, 3, 4, 5, or 1, 2, 3, 4. Now 4 is shorter, but do you see that it includes more functional groups? I get carboxylic acid plus the ketone, versus if I go down here, I only get the carboxylic acid. So you try to include all of your functional groups in your parent chain. So if I have 4, how do I name 4? Bute. So it would be butanoic acid. Okay. How do we name a carbonyl, the ketone? Do you remember? Oxo as a branch. And see, carboxylic acid is always functional group number 1. So 1, 2, 3 oxo there. And then what is this group here called? Propane. So as a branch, it's propyl. So we have 3 oxo, 2 propyl. And why does oxo go first? Just alphabetical order. Correct. That would have been like 3-hydroxy. And then the new one we're going to learn today is when we have an amine group. As a branch, it's called amino. Kind of think of like amino acid. So whenever it's the parent chain, it's called an amine. But as a branch, it's an amino. Okay, so the longest chain here, we have 1, 2, 3, 4, which is called what? Bute. So butanoic acid. And then 1, 2, 3, 4. So on carbon 4, we have, what did I say this was called? Amino. So 4-amino butanoic acid. So we have oxo, which is which one? The ketone. What is OH called as a branch? Hydroxy. And then NH2 is called amino. let's do one more of these. So
So what's the distinguishing factor between the aminos compared to
here, this is a branch. Carboxylic acid's more reactive than an amine. So it would, when you're looking at priorities, it would get the number one priority over an amine. So whenever an amine is a branch, so it's not the number one priority anymore, it's called an amino. But whenever it is the parent chain, so the only thing that's more reactive than it right now is the carboxylic acid. So then everything else, it would have ended in amine. So as a parent name, it's amine, but as branch, it is amine O. So pretty much the only time you're going to see amino would be with a carboxylic acid. So let's look at this one right here. We have 5 carbons, which is called pentanoic acid. And this pH, what is pH? Not phenol, but phenyl.
Oh, okay.
And what is phenyl? Benzene. So 3-phenyl pentanoic acid. As a branch, they call benzene phenyl. But what's ironic is that if it's CH2 phenyl, they call that benzyl. You'd think it would not be like that. Anyway, so 3-phenyl, and usually it's easy to see because they usually just have a pH on there, so you'll know it's phenyl. Anyway, so that's how you do it. So nothing really has changed. It's just now you're going into an oic acid. And you don't even have to worry about the number of the carboxylic acid because it's always number 1. Okay, so what is it called when we have an OH off benzene? Phenol. What is it when we have an NH2? Aniline. And then here, now if we have a carboxylic acid, it's called benzoic acid. If we look at kind of some of the naming here, here's our benzoic acid. And then how do we name NH2 as a branch? Amino. So you could say 4-amino benzoic acid, or just P. What does P stand for? Para, because they're 1,4. Here, again, we have benzoic acid, all right? And then OH. How do we say OH as a branch? Hydroxy. So we have O, hydroxybenzoic acid, and O stands for ortho, because they are 1, 2 apart. And then you could look, again, the benzoic acid, and how do we name this branch? Methyl, and then is it an ortho meta para? Para, so we put P. They don't have a meta on here, but meta, what do you think? 1,3, but what letter would you use? M. And if you ever see this, I just want to show you. You can have 2 carboxylic acids. And this is just a dioic acid, meaning di meaning 2. All right, here's the basic structure. I'm going to draw it on here of a carboxylic acid. This one's called formic acid. That's the common name anyways. If I was going to give the IUPAC name, so the official name, how many carbons here? 1, so I call that, methanoic acid. This is like what's found in ants, you know, when they bite you and it hurts and it itches. That's formic acid or methanoic acid. Okay, so let's look at the structure here. If a nucleophile was going to attack this, make a bond to it, where would it attack and why? The carbonyl carbon, and why right here? Not electronegative? Electropositive. Because that one has the electropositive, and what causes that? The oxygen there, and there's also oxygen here. Say you have two electronegative atoms pulling electron density away, making this carbon right here very partial positive. Does this have hydrogen bonding? Yes. So will that increase or decrease the boiling point? Increase. For this carbon right here, so this, what is the hybridization? sp, sp2, sp3, sp2, because of the double bond. Solubility is just like any other structure. So the longer the carbon chain coming off of here, so you know something like this, do you think you're going to find it more in the organic layer or the water layer? Organic, because most of it is organic. Now the shorter this is, the more likely it's going to be found in the water layer. So it says on this slide here, with up to 4 carbons, acid is miscible in water. So longer than 4 carbons, it's more in the organic layer. 4 carbons or less, it's more in the water layer. So again, that was just experimentally they realized that. So basically the longer your carbon chain, the more likely you're going to find it in the organic layer. Okay? Do you think this is acidic? Yes. Look at the name of it, right? It has acid in the name of it. So it's definitely acidic. Which hydrogen is your quote-unquote acidic hydrogen, the reactive one? The one bonded to the oxygen right there. If we look at like a regular alcohol, so let's say CH3OH versus formic acid again. Okay. The pKa of, let's see, alcohol is around 16. The pKa of this, 5. Okay. Which one is more acidic? Oh. The carboxylic acid. Okay. What makes it more acidic? They both have the alcohol. They both have the hydrogen. What about the second oxygen? Well, more importantly, what about after it reacts? There's resonance there. So it stabilizes my product. So anytime this is my product, that's after it reacts. Okay? If you can stabilize your product, that makes the reactant, the starting material, more reactive. Because it goes towards greater stability. So if you stabilize this, it makes this tend to react more readily. So because of resonance, it says that carbonyl oxygen there that allows it to resonate. All right, then we can also look Let me pull up this slide. It'll be easier than drawing it. Okay. Now let's look at these here. So here is a regular, this is acetic acid. Okay. So it's CH3, COOH. The pKa is 4.74. Now when you put on 1 chlorine, it is now 2.86. Put on 2 chlorines, it's now 1.26. Put on 3, it's now 0.64. So why do you think these chlorines are causing it to be more acidic? They're electronegative. So what is electronegative atoms like? Electrons. So it's pulling the electrons closer to it. So when we're thinking of an acid, what does an acid give up? Which? Hydrogen. Okay? So the easier it is to give up a hydrogen, the more acidic you're going to be. Okay? So when you have a chlorine here that's pulling the electron density, so think about this bond here, is made of electrons, and it's basically like a magnet. It's pulling these electrons closer to chlorine. So do you see that now they're further from hydrogen? So if those electrons are further away from it, that bond is weaker, a lot weaker. Okay? And you can see basically the more chlorines you add on there, it basically makes the magnet stronger in a way. Okay? So now it's pulling that electron density with more intensity. So this bond between O and H is even weaker, causing it to be more acidic because an acid gives up a hydrogen. And then what's going on down here? Each of these have 1 chlorines, but what's the difference between them? The distance. So do you see that this chlorine's 4 away, 3 away, 2 away, and as you get closer, it's stronger. Why do you think that? Just distance. Yeah, have you ever put 2 magnets together? Do they feel stronger when they're far away or really close? When they're close. And so that's what you're seeing. The closer you put that chlorine, which is attracting those electrons, the more intense that attractions are. So if you ever want to make something more acidic, they tend to put halogens on there. And you can make them sometimes into what they call superacids. Same thing's going on here. Electron withdrawing groups. So that just means they're pulling that electron density towards it. It makes these carboxylic acids more acidic. So you see here, this is a donating group. So it's donating electron density. So it's making that bond kind of stronger. So it's 4.46. Take that electron donating group out, now it's 4.19. Because again, it's a donating group. Donating electron density makes a bond stronger in that case. Here, this is electron withdrawing group. Now it's at 3.47, so it's more acidic. Electron withdrawing group here, 3.41, and then here, 2.16. And this has to do with resonance that makes it more or less acidic. This one's with distance. But basically, you put electron withdrawing groups on benzene, just like with the chlorine, and it causes it to be more acidic for the same reason. Anyway, so this is just showing you when you have a lot of halogens on there, you see the acid pKa gets really low, which means it's a strong acid. You see like fluorine. Fluorine's the most electronegative atom, right? So that's going to be your strongest magnet. So you see when you start putting fluorines on there, you get the lowest pKa. This is just to show you Kind of like, we were looking at aspartate and glutamate, remember? And they're sometimes called aspartic acid and glutamic acid. So this is just the same thing here. So I have a carboxylic acid, okay? I'm going to react it with a base. What does a base do? Takes off a hydrogen. So now it becomes this. And this is called a carboxylate. And that's kind of like, glutamic acid, which would be the acid form of it, versus glutamate, which is the carboxylate form of it. So the 8, anytime you see 8, that means it's in the ionic form of it. It already lost its hydrogen. Now, of course, you can go back to the acidic part there. You put an acid in there, and it'll go back to the carboxylic acid. But anytime you hear something called a carboxylate, you're saying that your acid reacted. Okay? And usually in biochemistry, they call carboxylic acids carboxylates because in your body, for the most part, they've already reacted. The only exception would be in your stomach, but everywhere else, it would be a carboxylate. So a lot of times, again, in biochemistry, they refer to a carboxylic acid as a carboxylate, which is pretty much the same thing. You're just saying it's reacted. Let's just show you more of that. Don't worry about the naming. Just note it ends in 8. Okay. The carboxylates, a lot of times we see these as your soaps. And what happens here is, let me show you this. So here's a fat or an oil. This is how you make soap, or like back in the day when they would make soap. You get your fat or your oil. A fat or oil just means you have a very long carbon chain. Okay, they call those your fatty acids. I don't know where that came from, but just know when they refer to something as being fat in organic chemistry, that means they have a long organic chain. Okay, so what happens here, what are these? So I have a carbonyl O carbon, ester. So fats and oils are esters, okay, with this long carbon chain. Then what they do is they react it with a base and water. Now what happens, I think, when we have OH in there, it's going to attack the carbonyl. Electrons go up, come back down, and then we kick off the O carbon group, which is this here. And you see that there's 3 of them here? 1, 2, 3. So all of these, you see this section right here? That's the leaving group for all 3 of them. And so do you see at the end, it's gone, and that O group right there is from the OH. Okay? And these are your soaps. And how this works, okay, so you have like soap scum and stuff. Some of the things in your shower are not water soluble, okay? Maybe they're organic or maybe whatever. They're not always water soluble. So you have these long chains like this, okay? This part right here, because you clean your shower, well, you might put like soap or something in there, but you use water, right? To maybe rinse it, or maybe the rag is wet or something. But anyway, water is involved somehow to rinse out the soap or whatever. This part right here is attracted to the water, okay, because you have your electronegative atoms, a charge, everything there. But this part right here is attracted to what? Anything organic, anything basically insoluble to water, okay? So what you do when you get a lot of these, anyway, they form like a bubble almost all the way around, okay? And they'll go, and there's going to be, millions of these. Now the inside right here, this is the organic insoluble part, okay? So you're going to get your soap scum, let's say. It's going to be attracted to here. Now normally, if you just use water and only water, soap scum won't do anything. It's not water soluble, so it's going to stay there. It's hard to get rid of. But when you use these, the soap scum's attracted to this organic portion, and then what happens here, the outside of it, we'll call it like a shield, is attracted to the water. Okay? So what can happen, it traps the soap scum inside, but then is still able to be removed by water because the outside is attracted to water. So think of it, like a cage. The cage is in the soap scum, and then the outside takes over, so you can just wash it down the drain. Anyway, so that's how soap works. Some important acids that you might be familiar with would be like acetic acid. That's in vinegar. A lot of your fats and oils and stuff, those are from fatty acids. Benzoic acid, this is used in different drugs and preservatives. And adipic acid is made in nylon 6,6, so like pantyhose. I believe benzoic acid, I can't remember, I think it's found in a lot of like acne medicines or something like that. Yeah. So you're familiar with that there. Okay, and phthalic acid is in polyester. Okay, if we're looking at IR and NMR, so how, like if we made a carboxylic acid in the lab, how could we confirm that? Well, if we look in the IR, we would see a carbonyl peak around 1700, and then we would see that alcohol peak, that really broad peak around 3000-ish. So this is a pretty simple functional group to find in the IR. It looks nice. You're going to have your pretty alcohol and carbonyl peak together. In the NMR, it's also nice. So here's one. Here's your 1700 peak, and then here's your giant alcohol peak here. In the NMR, this OH, this hydrogen from the OH peak, comes in at 11.2. Remember, it's the only thing that comes in between 11 and 12. So if you have a peak at all in the NMR that comes in between 11 and 12, the only thing it can be is carboxylic acid. So that's also really nice too. So if you want to confirm, your IR, you're like, well, I'm about 99.9% sure this is, a carboxylic acid, and you can run the NMR. You have a peak between 11 and 12. You'll know 100% it is carboxylic acid. So you can look at all of these peaks here, but that won't help you as much as this one to confirm it. Oh. All right, synthesis. Let's look at a couple of these. I just want to show you some of the old ways that we already know how to make carboxylic acids. We've made them before. And the first one would be here. I have a primary alcohol, so how many times can this be oxidized? Twice. So it's the primary one, the one at the end, that can always be oxidized twice. And I put it in here with this. Is this strong or weak? Strong. So it'll oxidize it all the way to what? Carboxylic acid. So a strong oxidizing agent with a primary alcohol turns your primary alcohol into the carboxylic acid. So we've already done that one before. Just want to remind you of it. Can you do that with a secondary alcohol? No, there's not enough hydrogens there. So this only occurs with primary alcohols. We also did this one. Let me draw this one out. KMNO4. Do you remember, is that the good surgeon or the bad surgeon? Bad surgeon. So what did it turn our hydrogen into? OH. So I would cleave this because it's a surgeon. And what do I always cap things with? What's my Band-Aid? Oxygen. And then since it's the bad surgeon, it cuts off hydrogen and turns those into OHs. So I've made 2 carboxylic acids. So you see here, I cut it. You see methyl, hydrogen, methyl, and then hydrogen turned into OH. Then over here, on this side, I have methyl coming up here, and then hydrogen, which is turned into OH. So what's the requirement? If you want to make a carboxylic acid with this, what do you have to have? Yeah, you have to have hydrogens. So if I had this with KMNO4, do you see there's no hydrogens there? So whenever it cleaved it, it would just make 2 ketones. Yeah, so if you wanted a ketone, let's say like that, and then a carboxylic acid, you would have this. So the right or the left, which one would make the carboxylic acid? The right, because you have to have that hydrogen there. The hydrogen is what turns into the alcohol, which makes the carboxylic acid. So the left side, you see, would turn into the ketone, and then the right side turns into the carboxylic acid. All right, and then the last one, since it's very similar, and then we'll take a break. Okay, so this one you can use KMNO4 or ozone. They're going to do the same thing. Both of those are what? They're oxidizing agents, surgeons. So what do they cut when they cleave? The triple bond. And what does it cap both ends with in this case? Well, I have three bonds. 2 of them will make the carbonyl, kind of like up here. And then I have that third bond, and what does the third bond turn into? Not water, but OH. Okay? So if I show you, 2 of the bonds from the triple bond become the carbonyl. That third bond from the triple bond becomes OH. So do you see 1, 2, 3 from the triple bond? And then you see there's a methyl coming off of there? That's that methyl. So on the other side, methyl, and then make carboxylic acid. So all you need to do, let's say this chain was longer. You would have your chain there. Let's see, 1, 2, 3, 4. 1, 2, 3, 4. And then where the triple bond is, that's where it turns into the carboxylic acid. So the difference between these two, for a double bond, you have to have hydrogen. For a triple bond, you don't have to have hydrogen, because either way, it's going to turn into a carboxylic acid. But both of them cleave. Okay, so we have oxidation of a primary alcohol, and then the other two are the cleavage. So either cleavage of a double bond, and what's the one requirement? Hydrogen. And then cleavage of a triple bond, which there's no requirement there. It'll always cleave into the carboxylic acid because I have the 3 bonds to make it. Versus the double bond, you see I only have 2 bonds there. So the only thing it'll make the carbonyl. All right, so let's stop there for the new material for now. Let's take a break, and then we'll start reviewing for 18 and 19. All right, let's review a little bit of this. So let's start chapter 18. And we will start, I'll just kind of go in order of everything. So let's do naming first. That's an 8. It was an OH. Okay. What's the longest continuous chain here? 4. 1, 2, 3, 4. So that's bute. And then what is it? Al. Okay. And what else do we need to name? Oxo, which is 3. 1, 2, 3. 3. Oxo. Anything else? Nope, that's it. What about this one here? What's the longest continuous chain? 5. So pent, and how is it? Own. So pent and own. Where is it located? 2. And what else is in there? Methyl. 4. Methyl. Why do we put a number on the ketone but not on the aldehyde? Yeah. Aldehyde's always carbon number 1. Ketone could be anywhere in the middle of that molecule. So you have to put where it is. You know, there's a difference between the ketone being on this carbon versus this carbon, right? This would be carbon 2, it would be carbon 3, and you have to specify that. Okay, let's go over the reactions. Let's do predict the product first, and then we'll go through and do the mechanisms you need to know. And then if we have time, we'll do some synthesis. Okay. Oh, wait. What is this here? Oxidizing agent. So what do? I oxide. So I make more bonds to oxygen. So my alcohol will turn into the carbonyl. What is this one here? It's a not reducing agent, oxidizing agent. How many times does it oxidize? Once. So this alcohol will go to a aldehyde. It makes the carbonyl. So if we review, a secondary alcohol, which would be like this alcohol right here. Do you see it's connected to 2 carbons? Whenever you oxidize it, no matter what you put in there, what oxidizing agent, you'll always make a ketone. primary alcohol, like this one right here, you see it's only connected to one carbon. This oxidizing agent will make what? I'll always make a carboxylic acid. And then PCC, just like we did over here, will make the aldehyde. So the one that you have to really worry about, would be the primary alcohol, because depending on what oxidizing agent you put in there, it'll either make the carboxylic acid or the aldehyde. Okay, we did this one. Is this one the good surgeon or the bad surgeon? The good one? So do I do anything with hydrogen? No, I'm going to leave it there. Okay? But it cleaves the double bond and caps it with oxygen. So depending on what I have coming off the double bond, I can either make ketones or aldehydes. The aldehyde, what do you have to have? An H. You see the one with the H, that's what made the aldehyde. And then for the ketone, you need 2 carbon groups. It can be any 2 carbon groups, but just carbon groups there. I also did this reaction. What does this put on benzene? The carbonyl. And where is it connected at? Where the chlorine is. So you see the chlorine was connected right here. Now the benzene is. Okay. Now I have a triple bond here. So what am I adding onto here? What functional group in general? A what? Not an OH. It's going to rearrange and it'll form a carbonyl. So deciding where does the carbonyl go. And the top one, anti-mark, so the carbonyl goes to the end. Okay, and then this one is mark. So now the carbonyl will go in the middle there. And this happens with a triple bond. With a double bond, you're adding the alcohol. But the triple bond, it turns into the carbonyl after it rearranges. All right. What will this do? What this carbon lithium group, what happens with that? It what? Say that again. Yeah, that makes that carbon a negative charge, just like the Grignard. And the OH will end up leaving as water. So my final product, OH left, and I just added 1, 2, 3 carbons. What about this one here? What's the difference? Yeah. Yeah, so the copper lithium is a little bit weaker because the halogen is really strong. So what's my leaving group here? The chlorine. And then what replaces it? The carbon group. So where the chlorine was, now I put my carbon group there. All right. What on step 1? What is that? No hydride. Hydride. And how many do I have? I have 1, so it's going to react 1 time. What is my leaving group on here? Chlorine. So chlorine's leaving, and it's going to replace with H. Okay, so what happens here? What is this? Grignard? And so that makes that carbon negatively charged. And where does it attach itself? This carbon right here. And then at the end, after the water reacts, the nitrogen is replaced by the 1O. So I have, there's my carbon. The Grignard puts a 3-carbon chain link on there, 1, 2, 3. And then the water replaces the nitrogen with the oxygen. So in the end, what did I just make here? A ketone. Okay, the first one, what does that do? How does it react? Yeah, the water will add an alcohol, and what will the carbonyl become? Yeah, it'll also become an alcohol. So when you add water to a ketone or aldehyde, you get your diol. 1 OH is from the water, and we'll do this mechanism. The other OH is from the carbonyl. All right, what about this one here? Yeah, you'll put 2 OCH3s where the carbonyl is. And what about the last one? Put your protecting group on there. Okay, let's look at this one. What type of reaction is this? Wittig. And what happens in a Wittig? Well, it is gone, but it adds the carbon where the oxygen is. So you'll get here. Now instead of putting oxygen, you're now going to put this carbon group. Like that. This is a 2. All right, what will the top one do? Yeah, where the oxygen is on the carbonyl, I'll now put my nitrogen. So the carbonyl was right there. Now I'm going to put in, and what is the nitrogen connected to? OH. What about lithium aluminum hydride? Not oxidize, but reduce it. Yeah, only the aldehyde, and it'll turn it into a alcohol. So the carbonyl turns into the alcohol. See, there's less bonds to oxygen, so we reduced it. I think we reduced the number of oxygen bonds. And it does not reduce this double bond here. What about H2 rainy nickel, though? Resolve it. So my double bond becomes a single bond, and my aldehyde will become alcohol. What about zinc hydrochloric acid? It reduces, but it completely gets rid of the carbonyl. So it doesn't turn into an alcohol. I mean, it erases it, essentially. So you have 1, 2, 3, 4 carbons in this chain. So 1, 2, 3, 4. Carbonyl is completely gone. Not the carbon from the carbonyl, but the oxygen. What about this one down here? Nitrogen sandwich. What does it eat? Carbonyl carbon. So it's the same exact thing. The only difference between these two, remember, is just that one's in acid, this one's in base. But the result is the same. It gets rid of that carbonyl oxygen. So those are all of the reactions from chapter 18. There's quite a bit of them. So now let's kind of look over the mechanisms I could ask you about. So those are all the examples of predictive products. If you can do those relatively easy, then you're on a good track. You should be fine with the predictive product. They're going to be on that level. Okay? If you had trouble with any of them, go back and review them again. You know, cover up our answer and see if you can get the same thing on your own. Okay? Okay, the first mechanism . Okay, what happens in the first step here? Yeah, so this is a negative charge here, and it's going to make a bond right here to that carbonyl. And then what happens to the double bond? It moves up to become a lone pair. So you see, my oxygen is now a single bond with an extra lone pair, and I just added this carbon chain here. But let's look at my product. Do I have the OH on there anymore? Nope. And how is the oxygen bonded? Double bond. So how do we make a double bond? Yeah, move the lone pair back down. And then what am I going to kick off? OH. And what will it grab? Hydrogen. Let's do another page. Do you have this part? Okay. Okay, what happens here? Same thing. So CH3 is going to attack carbonyl carbon, and then these electrons here will go up. Okay. You see chlorine's gone, oxygen's double bond. So what do I want to do to achieve that? Lone pair comes down, chlorine leaves and grabs hydrogen to give final product. See, those mechanisms are pretty much the same exact thing. It's just you have a different leaving group, really. Okay, what is our first step here? Yeah, CH3 attacks this triple bond, this nitrile carbon. And then what happens to the triple bond? To skip a step, it could grab what? It could grab a hydrogen. It does move to nitrogen, okay? But pretty much at that same instant, it's grabbing hydrogen. Also, just look here. By the end, we need to have an NH4. So we just need to have it keep grabbing hydrogens there. All right, then what is my next step? Yeah, the water from, the oxygen from water attacks this carbon. And then what will happen to the double bond? It grabs another hydrogen, leaves to grab a hydrogen. You can put the electrons down from oxygen, which forces, a single bond to break and grab a hydrogen. And what's my final step? So I formed NH3. So what do I need to do? Yeah, I need to grab another hydrogen to form NH4, and then DC my final product also, that oxygen doesn't have that hydrogen. So this amine will grab this hydrogen, pull it off, leaving its electrons with oxygen. All right, what's the first step here? Oxygen is going to grab the hydrogen since the acid is in there. Do you see that it's becoming that OH now? And then what happens? Yes, the oxygen from the water will now make a bond to the carbonyl, which will cause the carbonyl, one of the bonds from there, to go up to make a lone pair. So you see I have an OH here, and I have water here. What do I need to do for my final step to make it look like the product? Magic water will take off a hydrogen. And this is going to the oxygen. Again, studying these is just drawing them over and over and over again. And rationalize to yourself why you're drawing the arrows. You have this nucleophile, it's attacking this electrophile. Carbon's attached to electronegative atom, gives it a partial positive. Anyway, so understanding why it happens will make it easier. So if you get stuck, you could rationalize it on the exam. Think about what usually happens. Okay, what happens in the first step here? Yeah, oxygen grabs hydrogen. Okay, so let's look at our product here. Do you see I have my little hat on, my protecting group, coming from this? Is this carbonyl oxygen on there anymore? No, so what does it leave as? Water. Oxygen will leave as water. Okay, so I already have an OH, so I'm getting closer to that water. What do I do now? Yeah, the protecting group attacks the carbonyl, causing those electrons to go up. So this double bond OH now becomes a single bond OH here. Now we have this OH on there. What's the best way to make that leave? These electrons could push down that forces this to leave, and it'll grab that hydrogen as it leaves. So that leaves us water. Yeah, so then there's oxygen over here dangling off. It's still a good nucleophile. So it's going to attack this new carbonyl we formed, causing those electrons to go up. Yeah. So my final step, you see I'm almost there. I just need to pull that hydrogen off. So I can use this water that came off over here, grab that hydrogen. So again, I think the hardest step to remember is right here. You have to remember to push those electrons down to make OH leave as water. All right, and then the last mechanism of this chapter that you're responsible for is the Wittig. Remember that sometimes you can see the Wittig like that with a carbon double bond to phosphorus, or sometimes they do the single bond. Those are resonance. If I move those electrons right there, that makes a double bond. So don't ever let that fool you. The Wittig can be drawn either way, and I've seen it both ways in textbook. I've seen it both ways in sampling. So. Okay, where does this carbon attack? The carbonyl carbon. Okay, which causes these electrons to go up, right? Now, what happens here with the Wittig? Yeah, the oxygen electrons will make a bond to the phosphorus. So do you see this is a negative, and the phosphorus is a full positive? So they're attracted to each other, so they literally will just go and make a bond there. Oh, forgot to put the product. Okay, in my product, my CH2 is bonded how? With a double bond. So what I'll do, and you see the phosphorus is not on there anymore. So I'm going to break the carbon-phosphorus bond and literally just move it to there, which would make a double bond. Now let's look how the oxygen and phosphorus are now bonded. They have a double bond. So let's break this one because the oxygen is not on my organic product. So let's break it, move it to there to have a double bond oxygen-phosphorus, which gives me the final product. So how do you know to form the box and then collapse it? It's just anytime you see the Wittig, you'll see with phosphorus and the 3-phenyl groups, you will do that. Okay? So knowing that is just memorizing that Wittig always does that. So that's a lot of your mechanisms. Some of it's just, knowing the trends, the nucleophile, attack the electrophile. In this case, the carbonyl, those electrons will go up. So that stuff will always happen. But it's little steps like this that just come with practicing, knowing that every time I see the Wittig, this occurs. So some of it's just practice and memorization. So that's all of the mechanisms. We don't have time to do synthesis today, but on Monday, we'll work out some synthesis problems, and then we'll also review Chapter 19.